Hello, my name is Dan Hansen and I'm a Technical Marketing Manager with Cisco's Data Center Product Group. This video is part of a series that is intended to show some of the unique advantages made possible by Cisco's server offering called the Unified Computing System, or UCS for short. This particular video we will talk a little bit about applying very low-level adapter settings into a stateless service profile and some of the benefits of this. So as a baseline today, to manipulate some of these settings, many of our administrators have to go in and use varying methods by operating system, sometimes by adapter vendors, and whether it's done in the OS, in the kernel level, or in option ROM at boot time, they set up or customize parameters at a very low level on these adapters. We'll show some Linux and some Windows examples of these type of functions, but then it gets back to why should we care? And really what we want to talk about is being able to configure a server to optimize latency, perhaps some throughput, establishing maximum transmission units or more data per packet kind of environments, even out the processing of this flows on the compute node itself, ease rollout of boot configurations, things like that, easing these steps are where we're going at. So to start this out, we'll basically show bringing up an example of a storage option ROM, where administrators might have to go into these devices and make some changes. Now one school of thought is simply, hey, let's leave everything as generic compute and leave everything at default, and that's good enough. And that's an answer when it's too operationally complex to actually do these optimizations, or you don't have a solution to be able to do it. So what we're going to show here is an example again using a tool from one of our partners, QLogic. And you can go in and you see where we set up some of the option ROM values in a pre-boot environment. And we do this per adapter. Have to search out which adapter it is. If we're going to do a boot from SAN type setup, we would then go in and scan what's available, what we can see, define WWNs and LUNs to actually boot from. If we wanted to, we could get deeper into some of the more granular and detailed configuration items. And all of this is done on a server-by-server basis. Some efforts to script some of this to varying degrees of success, but it can relay a lot of an inability to actually programmably define some of this and be an inhibitor towards some of the goals of stateless compute and high-velocity service turn-up, turn-down modification. As another baseline example of the legacy environment, let's bring up a Linux host here. And you can see, and just a simple example is setting the MTU of an adapter, and where we go in, do this command, and you see that some of these basic settings are configured. We'll go reset this just before moving on. Again, this is just on a standard network adapter that's out there. Now, if we take another look, we can use ethtool, tool within Linux, to actually start looking and change coalescence parameters, or in this case, view them. Now, interrupt coalescence is just one common example where, as packets or as data comes in off the network with the storage, what we're going to do is moderate the amount of interrupts such that, for example, not one every packet is raised, and maybe I group packets before I raise interrupts to the CPU. It's a trade-off of network flow and latency versus processing resources to be able to handle that information. And many operations and customer environments, they're looking to optimize this. Another one is when we take a look at some of the sizing, the buffer sizing, based on receive buffers or transmit buffers on the network. You can see in the traditional Linux kernel, we're going to, one common method is to manually set a file in the system that instructs the kernel to configure the adapters to support or change some of their I/O characteristics. So this is another thing that customers many times do if they need to get some of these additional performance characteristics out of their device. So another example here that will show a little bit is taking a look at how the interrupts are actually spread amongst the processors, the cores, and the threads, where they actually might be living from a CPU perspective on the server. So you saw this example. This server has 16 individual threads that are cores that are actually running, and you'll see how they're spread about. But if we take a look at some of the network I/O parameters here, and we take a look at the offload capabilities, you'll see we have a receive checksum, transmit checksum, segmentation offload, large receive offloads. A lot of these devices we can enable or disable on the kernel level. And again, this might be scripted in some cases. Now we'll jump back to Windows to show kind of a similar type of settings, where we would take a look at potentially what MTUs we have turned on this type of a host, and if we want to make modifications to some of this. Another one is we can start looking into the TCP stack and say, do we have receive side scaling turned on, some of these other capabilities, ECN for collision or for back pressure. And you can see on here when we do some of these things, to spread interrupts amongst the cores so that you aren't stuck with one core that is handling all I/O load. Things like that can go towards optimizing. So what we're going to show here is in UCS, we don't need to go with those paths. What we can do instead is within a service profile, as you see, I drill down on my storage adapters and my data adapters. I have adapter policies that are put here, and QoS policies, various policies that are applied, in this case, to the storage and Ethernet within a service profile. So we're not simply taking a small subset of what might be configured on a server and applying it into this stateless infrastructure. What we're really trying to do is get a lot better coverage, a more complete coverage, including many of these low level details. So on here is an example of an existing default Ethernet Windows adapter policy. And here's one we're going to use for testing, just to show what impacts that might be arise here and answer the why not just take defaults in all cases. And this is one iPerf, and I can do the same thing in storage. You'll see through the same mechanism, the same API, the same programmatic infrastructure, you see I have the ability to tweak many of those parameters that I traditionally would have to go into a pre-boot environment and set up. And I can do that including whether I boot from an iSCSI target, whether I present this as discrete HBAs to the operating system, depending on hardware type and whatnot. And I can customize some of these, again, in this example, using my iometer in Windows. But we'll jump back to the iPerf example just because it's a fairly simple demonstration. We'll run through that now. So right now, the defaults that we have, I've essentially copied some of them over, and you'll see the policy that's set at a very low level. And I bring up my test tool, and it's the same policy on two hosts. And this is just going to send a flow from one host to another. It's on that interface, and it's just a single flow running, showing that we're running just about 5 gig per second, single flow out of the box. And this is really a limitation of the testing tool and the way this is set up and the way the processing is actually being done for this single thread on this server. So if I jump back to this policy and I say, you know what, on all servers making use of this policy, let's change from the 125 microsecond, which is maybe we want to get it smaller. Let's say in 25 microseconds, if there's existing I/O, let's raise an interrupt to the processor. So we could get a maximum of 40,000 interrupts a second that are spread amongst these 16 cores. Now, when I make these changes, you'll see here, during an appropriate change window, will apply these, and the server will restart to make the changes to these low-level policy changes in the server. Should I choose to change these beyond what I've set during the initial deployment time frame. So we show again the state machine where it's just going through and going to basically reprogram the adapters, and we're going to bring up the operating system on here, which I'll cut out the boot of that operating system, and we'll show you what the effect this can have on those servers. So after the device actually comes up, we can monitor the console to make sure it's actually booting. See the progress also, along with the FSM outputs. And we see that, okay, the server is up and ready, so we'll jump back in through our RDP session, bring up the server, and start the test tool again. Now, as we do that, we'll just start that same test, the single-threaded, point A to B, configure the tool for gigabits per second, the same host that we're going to talk to on the other end, and we'll just start the simple 10-second test tool again. Now, with these settings changed, the RSS settings and the coalescing time, now we're getting 7 gigabits per second. So we're almost 50% above where we were before. Now there's going to be a trade-off in CPU, but that goes into the baselining of an application in the customer environment. And we're now able to take these low-level settings, which often we didn't want to change because of the complexity involved and just the number of touches we would have to do. We can now make that part of a stateless profile here in UCS and make it an easy consumption model for a very powerful capability in optimizing the server resources to host a solution. To recap, configuring these low-level detailed settings throughout a server can be very challenging in many environments, and often people just don't do them because of the challenge. The UCS service profile concepts and the depth of coverage really helps this by easing the administration of this. This ends this UCS Advantage video, where we show how some of the unique capabilities in the Cisco UCS can lead to a simplified deployment model with much faster service turnaround to meet increasing demands of the business. Please go to www.cisco.com/go/UCS for printed collateral, including a brochure that highlights the information shown in this video. Thank you for your time.